Okay, good afternoon. This is Ray Seifert. I'm going to discuss a little bit about functions and primarily with Linux today. And I'll start by looking at this hello program, and for the moment I will pop this thing out. All right, and we've got some normal things here at the beginning of the function: push RBP, move RBP, comma RSP, and I've added a macro called frame that I'm using at the beginning of functions. And with Linux, it's going to start the, though we put the breakpoint on 8, it always stops the program right before it does a subtract. And I've got this thing set right now for 8 parameters for the function. I'm going to change this to match the reality of the thing and restart. The first number of the frame macro is the number of parameters to the current function. The main has argc and argv as parameters. The second number is the number of local variables, and I have none defined so far. And the third number is the maximum number of parameters that functions that this one calls, and this one calls write, which has 3 parameters. So when I do this, the macro doesn't generate any instructions. It does provide a definition for frame size, and the next instruction, subtract from the stack pointer frame size. Once I've done that, we have at that point satisfied whatever might need to be there, and the frame size value that you need to subtract is 0. And at this point, we can see where RBP is pointing and RSP, and they're pointing at the location on the stack where RBP had been pushed. And the previous value of RBP before main was 0. The value that's on the stack before this push is the result of a call instruction being executed. So it's the return address from this function, which is a rather goofy looking return address, but it's some address in a shared object file for something with a name like _start or something similar. I'm not sure what it is. Doesn't really matter very much. This address is incorrect. I just got this stuff working today, and I haven't noticed that before. All right, it's really at RBP plus 8. Now, I'll first go through the code here, and I'm setting up the parameters for the write function call. And the order is not very important when you're just going to put these values in a register. If you're going to put the values on the stack and you're pushing them, the order would be important. But my strategy with 64-bit assembly is going to be to adjust the stack frame to provide enough space to put any stacked parameters on the stack with a move instruction. All right, so the order won't be very important. So move len to EDX, which will be the length of the data to write. And you can see that len has an equate to $-MSG. Dollar is the current point of the assembly process. So $-MSG would be the number of bytes that are in this hello world, and then a new line character, and then I think that's all I've got there. Yes. All right. Execute that. Let's see. All right. You load that into EDX. There's EDX. All right, RDX, and it's a D, which is a 13. And execute the next instruction, load effective address of message into RSI, and I've got to bring back my registers. So we have RSI 602098, and the next one is move a 1 into RDI, and it already had a 1, but I wouldn't have known that. And the 1 here is the file descriptor for standard out. It's really a 1. All right. Then call the write function. It writes to the terminal window, and that's not visible at the moment. All right, so popping the terminal window into view, we can see that it printed hello world. The program works fine. Now, I'd like to explore a little bit more while I'm here with this frame macro. If we tell the assembler that we have 2 local variables, now when we enter the function and we do the subtraction, this RBP minus plus 24 is still not correct. I'm not sure where I screwed that up at. But in any case, we have the return address is correct, and now we have local 1 and local 2. The ebe.inc file defines local 1 through local 100. So you can have a lot of local variables, and it will define under Linux local 1 to be a -8 and local 2 as a -16. So if you want to access local 1, you can put instructions in there referencing it. So let's do that. How about we put a value into RAX 7 and then move that value to local 1, which we will always access as RBP plus local 1. After executing the subtract, the stack frame is basically correct, and later today I'll figure out where my 24 error came from. But when we do the move, here we put the value into RAX, and next we'll put it into local 1. So when we put it into local 1, we can see that it is what we expected it to be. We can observe it and do things with it. All right. Increment about EAX. Now, if I tell it to move EAX, is it going to move just 32 bytes, or is it going to move 32 bits or 64 bits? Let's see what it does. All right, incrementing RAX, ready to move it. There we go. So we moved an 8 into the low order half of the quad word. And if you really wanted to move the whole thing, it would have been necessary to move RAX. Now, when you move into a register, it will expand to fill the upper half of the register. But when you move a double word into memory, it doesn't do that. So let's move it and make it behave a little more rationally. Now we moved an 8 into local 2. Now with Linux, you're going to be pretty lucky with the number of parameters that are used. Oh, that's not right. I thought I'd move the cursor. Let's say we want to use 7 parameters for the function that we're in instead of having 2. Now you'll notice a little bit of difference. We've got current parameter 7 at this location, and this one has no name. The problem is, at the point that the function is called, the calling function is supposed to maintain things so that the stack address is a multiple of 16 bytes after you do the call and then do a push. So there has to be an extra word or extra quad word on the stack, and then current parameter 7. And you can use RBP plus CER PAR 7 to reference parameter 7 for your function. That's a little different from having called functions with 7 parameters. So let's tell it to run it with those values. Now we can see we've got new PAR 7. So if I wanted to move a value to new PAR 7, then I would do move and the new parameters are supposed to be referenced with the stack. And you'll notice there's a gap there. New PAR 7 is always just going to be 0. So new PAR 7. I'll have to run it again. Now we've got the 8 in local 2, and we're moving the 8 to be in the correct position on the stack for making a call and having parameter 7 be an 8. You'll notice there was a hole. If we make it have maximum call parameters to be 8, you see more or less the same thing, except now we've got new PAR 8 labeled in that table. All right. New PAR 7 is once again 0. New PAR 8 has the value 8, so you can see it is RSP plus 8 or RSP plus new PAR 8. And with my strategy for referencing the stack contents of this frame, the ones that are parameters to called functions are always RSP plus, and then new PAR 7, 8 on up to 100. And the ones that are either local variables or the current parameters are referenced with respect to RBP. RBP minus will be for locals, RBP plus will be for where the return address and the current parameters or the parameters for the current function are located. All right. Let me pop this thing back below. Ooh, that's exciting. All right. We get a little fun in this setup because we have 6 integer registers that can be used for parameters. RDI, RSI, RDX, RCX, R8, and R9. And I will be working and producing, I guess, another book that's going to refer to these registers as PAR1, PAR2, PAR3 on up to PAR6. I've gotten tired of remembering this sequence. Though I've done this one more than the sequence for Windows, I'm still a little tired of it. The floating point registers, that's not so hard to remember. XMM0 through XMM8. So if you can remember the registers, fine. If you've got difficulty remembering them, they can be found ready to be copied into your code using this little icon down at the book, down in the template toolbar that looks like books. And that brings up a window, and if I can make this just a little bigger, yes. Function parameters. So if I click on that one, it pops up in an HTML kind of window, this stuff, and it's already been copied to the clipboard. So at this point, I could go into the program and do Control V and get that copied in so that I then have it available in the code as a comment. It's tedious remembering crap like that. I found it really easy when I started doing assembly code, and I had a little less memory of these 6 registers. I found it much easier just to pop that into my file and then go forward. So you move what you want to into these registers up through 6, and then you call a function. And when you call a function, it puts a return address on the stack. Right? So you can see over here this return address. And then when you do the work to set up the stack frame, you push RBP, and the RBP is a pointer which would have been set for, if it had been set, for managing local variables and parameters for the previous function. And after you do this, you set RBP to point right here, and RBP minus will get you to the parameters to this function. Excuse me, RBP plus will get you to the parameters of the function. RBP minus will get you to the local variables of the function. And after you subtract frame size, then you're set up so that it's RSP plus new par 7 and new par 8 would get you to parameters 7 and 8 for a function that you might call. And as you can see there, if you're going to follow the rules correctly, you have to be concerned about maintaining the stack at a multiple of 16 in size. And I'm pretty sure that I've run into a few problems with things perhaps like printf or something that did something with the 16-byte function or 16-byte kind of instructions on the computer of some sort, and bailed out on me because I had the address wrong. The stack pointer was not on a multiple of 16. So if you've got the correct setup, in other words, if you're going to have one parameter on the stack, you need to subtract 2 from the stack pointer to make space for the one you want in one hole. And if you're going to have local variables, you've got a similar issue with local variables and new parameters. So the easy choice to avoid this trivia is to use the frame macro. So this one truly had 2 parameters, and I've added local variables, and I'm going to tell it that 3 is the stuff here, and I'm going to get rid of the code for new par 8. All right. Boy, that's so quick. I like this. This is a lot easier than sitting down and thinking about how many you want. If you're going to sit down and think about it, you would have to do something like, let's say you wanted to set I to be the first local variable. You would need to know that I should be equated to, where is the local variable? Minus 8. And then if you want another variable, k, you use equate with minus 16. And at some point, you would need to subtract a number from the stack pointer in here. that would accommodate your local variables and any parameters which have to be placed on the on the stack. That's not too common with 6 registers for parameters, so you might end up doing subtract 16 if you wanted to do that manually, and that would coordinate with I and K. But frame size is easier. All right. Now I want to switch this, save it. I want to look at the HAL version of this code, hello.hal. And it's the same business with frame. And I've got frame 201 because I'm using printf for my function call. So subtract frame size is going to end up subtracting 0. If you wanted to, you could just skip that and know that you didn't need to subtract. But if you have any doubt, it doesn't hurt you to subtract. You just waste one, basically one cycle of your computer's time. All right, load effective address of the message into parameter 1, and the accumulator is the equivalent of the REX register exit, XOR it out. That makes it 0 for 0 floating point parameters, and then call printf. You'll notice I've got %if not defined. This is the YASM syntax for dealing with testing whether a macro is defined. So if Windows is defined, that means that the EV code has figured out that it's running on a Windows system, and if it's not defined, it's running on either Linux or OS X. Either one, they have the same protocol. They need this instruction. Windows doesn't need it. But in this case, it's so simple that you can just leave XOR in there if you want to not bother with if not defined. All right. And we get another hello world, apparently with a small w. And we have the return address, which is again that address somewhere in here. And we have the same business. If you want locals, use local 1. It's not 1. Set it to 1. Then we can use local 1. And now we've got local 1 is available or viewable. You could use it without viewing it previously. And you could put a value in there if you chose. Now I want to look at a little more complicated program. See if I've got it as an assembly file. All right. Here's some of my code before I came up with this idea. So here's main, and you can see I've got n equated to 0, a to 8. That's interesting. Oh, and I've got RSP plus n. I didn't learn very well at that point that I should have used different stuff. All my parameters to all the functions fit in registers. So these are all references to variables that have been accessed with RSP, and it works. I'll go ahead and execute the code just to see what happens. All right, so there were a total of 9 of these variables defined, which went through 72 bytes, but to keep things on reasonable addresses, I subtracted 80. and then the program, you load into RDI, which is the register for the first parameter, the address of a prompt string, and zero out REX, and then call printf, and you can see that prints into the terminal window, enter the degree of the polynomial, which I'm going to enter 3, press enter. It's a little bit goofy, but it works. And then we're ready to call scanf. You'll notice you have to have the address of a variable to use it with scanf, so I'll do load effective address of RSI and RSP plus .n. If I were to do this today, I would change this code so that .n would be equated to local 1, and I would reference it with RBP plus .n instead of RSP plus .n, or either RSP plus or RBP plus local 1. If you got 9 variables, it's really frustrating to call them essentially numbers. That's almost as bad as having 8 registers with names which are totally meaningless to you. All right, so we zero out REX again, call scanf, and it should have placed the value into the stack. I could probably fake it out, though I wouldn't see A through PB on the stack, but I could fake it out a little bit. I'm sure that I've got my 3 there. Here I'm going to use it, so move this into RDI, and where are my registers? All right, I think I'll pop those in here. All right, so in RDI we now have a 3. And we're calling the create function, so we should use the next little icon, which looks like it's going into the middle of some braces. If you can see that icon well enough, it means it's to step into the code of a function. So we're going to enter the create function, and then push RBP, move RSP to RBP, and we need to, since we're going to call malloc, we need to be prepared. When you call malloc, you need to have the stack pointer on a multiple of 16, so you should set up the push and the move so that you're prepared for it. And then when you call malloc, when you come back from malloc, RDI might be destroyed. Let's see what happens. Yeah, it's got some other number in it. All right. Well, let's see. Shift left, okay. Shift left 3 positions, which makes it 8 times 3 or 24, 818 hexadecimal. Calling malloc when we're done, RDI is now 0, so the registers that we had for the parameters to the function would have been lost, right? Anything that you wanted to save from registers, you'd need to worry about saving it. After you call a function, REX contains the return value for the function, and in this case, REX is the address of an array. So I can do, oops. Supposed to be able to define a variable with that address. Now, and this one is our polynomial. I don't remember if this is a polynomial derivative array or not. I think it's for the derivative. So let's call it deriv. If I'm right, it'll be good fortune. And I believe that this is supposed to be an array of doubles. So 0 through 2. View the data, and I'll drag this in. And right now they're all zeros. All right. Then we hit leave, which restores RBP and RSP to what they were, and then return, and it moves REX to the stack in the location I've named .pp. I don't know why I wasn't energetic enough to call that derivative or something more appropriate when I wrote this code. Laziness is not really that admirable. PP doesn't mean much to most people. All right, so I move in back into RDI, and the next array is going to be for the polynomial itself. And a polynomial with degree 3 will have a sub 3 times x to the third power plus a sub 2 times x to the second power plus a to sub 1 times, anyway, it's 4 coefficients. So we increment RDI and call create, and I won't bother to keep track of this one, but I have another one, and I don't think I'll bother to create a thing for that. And then we're going to call create again. We have to load in one more time, this time add 2 to it to make an array of size 5 for a 4th degree polynomial, which is going to be the integral of the polynomial. And I call the integral capital P. All right, now we've got a prompt, and we're also going to print the number in. So we put the number in into RSI, and the address of that prompt array is in RDI. Zero out REX and call printf. And going back to the terminal window, it says enter 4 numbers for P. So I'll enter the numbers 1, 2, 3, 4, and hit enter. Then next I'm going to read these one at a time in a loop. So I start by zeroing out register ECX, which I'm going to use for I, and I save it onto the stack as a local variable named .I, and then I move into RDX and compare RCX and RDX. The reason why I'm saving it is I'm going to be calling printf, and register contents, lots of them are gone. So it's just easier to not depend on them. Compare them, jump greater than to end of the for loop. We're not going to jump to the end yet. We load the address of a scanf array, and then here we move into RSP plus .p. This is, well, it must be the one that we didn't save, I think, or didn't make a thing out of. That is the address that came back from malloc from one of those create calls. And then we do load effective address into this RSI for the second parameter to be the address of one double in that array. So when we're getting the address of that double, RSI is the base address of the array, RCX is the index. At this point it's 0, and multiply 8 times 0, so we get the value that's the base address of the array. And then call scanf, and it reads the value and it places it into memory. I doubt if this is the one that I've saved. I don't think so. I've got some glitches with my code anyway. All right. Keep going, and we restore RCX from the stack, increment it and save it again. Because RCX is one of the registers used for parameters. It's volatile. When you call a function, it's likely to get destroyed. Now, on the other hand, there are some registers which must be saved. Those would be RBX, R12, 13, 14, and 15 for Linux. And that's tedious to remember, but I've been doing this garbage a little while, so I remember it. I'll forget it in a week or two. But if you want to use one of those, they're guaranteed to be kept by well-behaving functions. But you're supposed to honor that same idea. So if you were going to use RBX, the appropriate thing to do would be early on in your function to save the current value of RBX into a local variable, and then when you get ready to return, restore the value from the local variable. Then you wouldn't have to, if you used RBX like that, you wouldn't have to use continual loading and saving of RCX. Might have been a sensible choice. All right, now we've got ready for the second variable. So when we get down to do the load effective address, RSI has 6054C0 and RCX has 1. So if we add 8 times 1 to that, we're going to get C8. So let's see if that is indeed what we get with load effective address. Yay, it's a miracle. Now we've got the right address for the second double in that array. If we call scanf, and it will read the 2. Restore RCX, increment it, now it's at 2. And we go and read the next one, and we've got an address ending in C0 for the RSI value. RCX is 2. 2 times 16 is a 10 hex, so it should make it to D0 for the address in the array. Call scanf. It reads the third number, which is a 3. We're not looking at it, but that's what it was. And we restore RCX, increment it, and we're going to be doing the last coefficient of this, and it compares 3 versus 3, and it's still not greater than, so we'll go in and do the body of that for loop. All right, RSI has C0, RCX has a 3, multiplying that times 8, we get a 24, which is a 1,4, so we should end up with a D4 as the last 2 nibbles of that value. Excuse me, not D4, it's a D8. All right. Load I one more time, increment it, we're at 4. We go back up to the top of the for loop and compare 4 versus 3, and it is greater than, so we jump to the end of the for, which next instruction after that is this. And now we're ready for the values for A and B. So we load the address of this AB prompt array, enter A and B, into RDI. And then we zero out that, we call printf. It says enter A and B. I will use 1 and 2 for my A and B values. All right, so we're ready to read A and B. And you'll notice I'm reading them both at once with a %LF. If you use F, you're reading a float. If you use LF, you're reading a double. So we load the effective address of the string into RDI. Then we load the effective address of A into RSI, and the third parameter is RDX. We load the effective address of B into that. Then we call scanf to read the 2 numbers, and we save those. We get ready to call the Horner function, which evaluates a polynomial. So we send in the polynomial that we want to evaluate, the degree of the polynomial, and the value you want to evaluate the polynomial at. So these two are integer parameters, either explicit numbers or an address. In the case of the first parameter, P is an address that was obtained from calling create, and N is just going to be a 3. So when we call Horner, we've got XMM0, view the floating point registers. I'll drag those into, oops. All right. And we can see that A is what we fetch from the local variable space and has the value 1. You'll notice it's XMM0. And that really means that we can have 6 integer parameters and 8 floating point parameters all passed into registers if a function had 14 of the appropriate types. Oh, I forgot to enter the function. I don't want to start over. I'll enter it next time. All right. So we go to print P of A equals, and it's 10. And then we're going to print P of B. And I'll try to do this appropriately this time. B is a 2, which is what we expected. And now I'll click on the button that means step into the function. So in the Horner function, and the first step is to move XMM0, which is a 2, into XMM1. So now we've got a copy of it, and we move into XMM0 a value from the array. RDI is the address of the beginning of the array, and RSI was the number 3 that we passed in, and that corresponds to the 4th number in the array. And if we're using Horner's rule, which I don't want to go into arithmetic, this is the one we need to multiply times the x first. So move that into XMM0. So we step forward, decrement RSI, and compare it. And then we're going to go through a sequence of operations where we're going to multiply XMM1, the 2, times the value that's in XMM0. And then we're going to add to that the next location from the array. So we get an 11. And then we're going to go back up. And if it's still time to do the operation, we're going to multiply it times 2 again to get a 22, add the next location from the array, and that's a 2, so we get a 24, and then we do it again, and we'll multiply 2 times the 24, get a 48, and add the, let's see, RSI is a 0, that would be a 1 in that location, so we get 49. And RSI is a 0, excuse me, it was a 0, it has been decremented, so it's a -1, and we're ready to return, and the return value is in XMM0. So now you can see why I switched and moved the original X value into XMM1. In that way, when I get ready to return, I have the value that I wanted to return in XMM0. I could have done it the other way around and moved right before the return, but I chose to move early to make it convenient. I won't go back through the Horner code again. All right, then we print P of B is 49. Right? Well, I took a little advantage here. I had previously called Horner, which left the value 49 in register XMM0, which is the first floating point parameter, and I set RAX to a 1, saying there's one floating point parameter. So that's how printf knows to use the XMM0. All right, now we're going to enter the differentiation function, and I've got the original polynomial is in P, so I move that address into RDI, and PP is going to be the address for the derivative array, and then RDX is the degree of the polynomial, the third parameter, called differentiate, and I don't know if there's a lot of value in going through more code, but we can see that this is pretty straightforward. We keep track of incrementing with I, and we multiply XMM0 by XMM1. XMM1 is 1. All these functions had a little funniness. This one does. I needed to add a 1 to some code, or to a value, and add it as a floating point number. The quickest way I could find to do it was to define in memory a 1. I could have moved it into a register at that point, but I didn't see any point in using a conversion function or a conversion instruction. And without going into the arithmetic behind it, RDI is the P array, and I'm loading P of I plus 1, and I is 0, so I'm loading this thing with RCX times 8 plus 8. That plus 8 gives us a plus 1 because we got the thing in 0. So we take the value that's in the array, that's a 2 in the second location, and then we multiply it times XMM1, we get a 1, and then we move that into the other array, then we increment RCX, and then we add XMM1 and XMM2. So before the loop, I had moved the dot 1 in memory to XMM1 so that I didn't have to move it from memory repeatedly. All right, so we do that a few times, and if anyone has taken a calculus class recently, they might remember how to differentiate a polynomial. And then we call the Horner function, and we're ready to print the derivative of the function at A, and then print the derivative at B. Here we're ready to calculate it at B, and then print it at B. And then we call the integrate function, which does another little set of manipulations of two arrays of coefficients. So standard procedure, we get 3 parameters here for the function. We call the function. I don't want to step into that function. And then we are ready to call the Horner function to evaluate the integral polynomial, using the Horner function to evaluate that polynomial. And we can print P of A, big P of A, the integral at A. And then we do the same thing with integral at B. And you might recall that if you subtract the integral function at the 2 endpoints, you get the area under the curve. So yes, we now have the area under the curve is a 26. It's a miracle. All right, do you have any questions about calling functions or how to observe what's on the stack frame, which I didn't use in this code? I'm not sure if everyone was here at the start of the session or not. I'll go back to using the hello code. This is the old style. This is what I thought about before. And reserve is sort of similar to give you some names, but frame, you can tell it the number of parameters, the number of local variables, which I'll set to 3, and the number of parameters, maximum number of parameters to call functions. And when you do that, I'll set a breakpoint on line 10. Oh, this one is a while back while I was testing this stuff. When you do this, this doesn't generate a subtract instruction. You need to subtract from RSP frame size, and frame size is defined by the frame instruction. So now if I go in here, I got RFP. Some of my playing. All right, I think it's finally ready to assemble. Yes. So subtract frame size, and we have some information over here in the stack frame, but it isn't correct if frame size is positive at this point. So after subtracting the frame size, now we have in here the return address is visible, which is an address in a shared object file, no doubt, in libc. And then we have local variables, locals 1, 2, and 3, which we've defined there. And there's a hole here. RSP is set to there. If I set it to 4 local variables, I get all right, so now we have local variables, and it's easier with this setup to manipulate local variables. So if I wanted to move, let's say, the value of the stack pointer into local variable 1, I'll run the program again. So now we can see that it's in local variable 1. It's also in local variable 2. I don't really know why. So this is the easier way to handle local variables. If you only got a couple of them and the code is not too long, just do RBP plus local 1, RBP plus local 2, and you can move a value onto a local variable. All right. See if somebody has sent me a message. No. Okay. I think that's enough for today. I want to do the same kind of stack stuff for stack frames for Windows, and eventually I'll dress them up for lots of folks. Bye. See you later.